Thank you everyone for attending today's webinar, The Right 3D Printer for the Job, brought to you by Design World. This is a first in a series of webinars on 3D printers, and we would like to thank our presenters for being here today and their respective companies, 3D Systems, Objet, Stratasys, and Z Corporation. I'm Leslie Langnaw, Managing Editor for Design World Magazine, and I will be your moderator for today's webinar. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, you can use the hashtag Right3DPrinter. We will also have a Q&A session after the presentations, so go ahead and submit your questions and we will ask them after all the presenters are finished. Our first presenter will be Buddy Byram, Senior Director of Global Marketing for 3D Printing at 3D Systems Corporation. Buddy has led the introduction of many products, including 3D Systems' entire project family of professional and production-level 3D printers, the Beflash personal 3D printer, and the vast array of materials used in these systems. I'm turning the mic over to you now, Buddy.
Okay, Leslie, thank you. And I welcome everyone for this, what I consider a very exciting topic, because as people begin looking for 3D printers, the number of choices that are out there can maybe seem a little overwhelming, and hopefully today's webinar will help people at least see where to go to explore what's just right for their applications. When looking at 3D printers, you really need to match your requirements to your budget and understand where you're going to get the best value and the best payback for your investment. We tend to look at 3D printers into different kind of use categories. At the entry level, we have open source systems that are really good for hobbyists, people doing experimentation who want to try a lot of different things, but don't have a very large budget to do that with. We have personal printers, which provide in-office desktop type convenience. They're affordable, easy to use, but yet can produce remarkable high-quality parts that can be used for a wide number of functional purposes. And then at the top end, there's the professional 3D printers. These are the ones that typically offer the best part quality and functionality and have the most versatility to serve the most number of application needs, and have the broadest range of materials and intend to have the best accuracies and precision. And at 3D Systems, we offer systems in each of these categories. When you look at your application requirements, it's important to look at your design process. And if you look at this chart, it shows to the left, starts with models, and then works across to final parts, where this is a representation of the needs that you have as you move from ideation and creation through your design process into pre-manufacturing and into final manufacturing. And the printers that are available in the marketplace today can serve one or more of these needs. And you need to look at what your particular area of requirement is and choose a system that can meet the most number of those applications. In this case, the Beflash and Bits from Bytes systems, which are affordable systems, can provide communication models that you may need early in the design process. But as you move through design, you have needs for prototypes. As you move into pre-production, you may need patterns. You may need to produce tooling, and then finally in-use parts. And how you use an additive 3D printer to serve those needs, what you can do with those is going to be dependent on the system that you select. At the very entry level of 3D printers, these are typically used for experimentation, or it's widely used for education purposes. A lot of engineering schools, for example, have adopted low-cost 3D printers. And these are available for as low as $1,200, $1,300. They're very affordable. They don't require a lot of service costs, and they're very simple to operate. And they're really good for people on a limited budget who want to experiment with 3D printing and want to be able to try out ideas, test theories, and really just have a great deal of interest in the printing process itself, in understanding that, and it provides valuable education and experimentation opportunities for that. Another application type that you may look at would be communication or concept models. Looking at attributes that are important for you in terms of performance and parts, if you're doing early concept models or communication models, you often want them to be lifelike models. It's important that your parts, really reflect the look and feel and design of the part. And so you need to be looking at surface finish. You need to be looking at fine feature detail and make sure that those things match what it is that you're trying to communicate. Another aspect here is a lot of times communication models are painted. And how you need to look and see how easy is it to paint these parts. Do I have to do a lot of sanding? Do I have to do a lot of preparation of the part to get a good high-quality paint job? Because you really want it to look like your final part and not inject, other things into the communication that aren't really a part of the final part that you're designing. Another thing to look at is build speed. You got to understand how the system builds, and just be aware that build speed in terms of Z height per hour is not the full picture when you look at build speed. You really need to be looking at build time. And on some systems, when you produce multiple parts, the system takes longer to build them. And you need to understand that. Know how many parts that you're going to need to build and what your typical use is. Will you have multiple people using the printer? Will you have crunch periods that you need to have a lot of instantaneous capacity? Do you build multiple component assemblies where you need to build 2 or 3 parts at the same time to really test an assembly? It's important that you look at build time of multiple parts on a build job on your systems, and we recommend that you look at build speed in that way. Example of a concept model, just real quickly, Thun Spa in Italy uses our Beflash system at 3D Systems to do figurines, and they basically use this to do painting to decide on the final colors that they're going to use on the part. And they like these models because they are non-pigmented, and it basically provides a blank canvas, and it readily accepts paint without having to do a lot of surface finish work. Another application that brings a great bit of value to engineers is form, fit, and function. As you move further into your design process, and you need to begin testing out these types of attributes. Here, you're really looking for accuracy and precision. You need to get systems that can meet your requirements, and the professional systems that are available today can offer accuracies, up to say plus or minus 1/1000th of an inch in terms of precision. And many of these systems also have some sophisticated software tools that allow you to even fine-tune the system to a particular geometry. So you want to look into the software tools and the ability for you to actually control accuracy and precision. You also want to look at the materials that the system runs. Material properties are very important. You need to look at them over a range of environmental conditions, because some of the materials in 3D printers are fairly stable, and others may not be stable either over time or over a range of environmental conditions. And then again, you want to look at part features. How well are the edges and corners defined? How well will pins, connectors, other features that need to mate together actually fit based on basically the resolution or the quality of the part features that are being produced. An example of a 3D printer application for functional testing is a company called Tima, and they have done this part. It's actually a rotor blade, and this part produced on a Projet professional 3D printer was used and actually survives destructive tests up to 14,000 RPMs. They were able to use these parts because they're out of tough plastic, and they were accurate and were able to duplicate the performance of that. So that's an example of a good functional test application. Okay, another application that might bring value to you is to look at digital manufacturing. Digital manufacturing can be either direct or indirect, and I put in this category two items here. One would be patterns and molds. You're pretty much going to have to go with professional production level 3D printers to do patterns and molds, mostly because of the accuracy, the surface finish quality, and also the material stability that you're going to need to really accurately do patterns and molds. You can use these either in prototype production or early production, and it can get you into production or into functional testing with final parts much faster if you have a printer that can do this. Another benefit that some printers offer, there are technologies, 3D Systems offers in our Projet line a technology that can produce wax parts. And producing wax patterns can allow you to do direct investment casting. So if you need metal components, either in a prototype environment or in early production, you can produce wax patterns and use the lost wax process to go directly from CAD to final parts. Here's an example of a company called DreamSlide that actually uses the wax printer, the Projet printer, to produce parts that they cast for their development process. And they're able to do testing with this. In this case, it was a part from this bicycle type product. And they were able to produce parts for functional testing to go on the final piece that were metal and did have a pretty high degree of complexity. And the nice thing about using an additive process to produce these casting patterns is that there's basically unlimited geometry opportunities, and it makes really fantastic castings that can be used in that purpose. Okay, and finally, as I'm, kind of winding down here, in addition to looking at your application, you need to understand the economics of the system that you're considering and getting ready to purchase. Obviously, system price is important, and it's not always the case, but I think it is a pretty common rule that the more capable systems are going to be higher priced. Obviously, that depending on your application, there may be low-cost systems that serve your needs very adequately, but you really need to understand your budget and see how the system price affects that. But there's more to it than that. You need to look at the material cost. Material cost is not just the cost of the raw material that goes in the printer. You need to understand how efficiently that printer operates. You need to understand how much material is used to build support structures. You need to understand how much waste is generated in the system itself. There's a lot of factors around part costs, and so be wary of quotes about standard cost per cubic inch. You really need to look at your own parts, You need to have your own parts evaluated by a professional that can help you understand what the true cost of material and is for that part. Also, service and maintenance. Often overlooked. People tend to focus on material costs, but material cost only ranges from about 30 to 50% of your total cost of building parts. Service and maintenance is a big one, and you really have to amortize that cost or expected cost over the number of parts that you build over a time period and build that into your cost model. Some systems have very little service and maintenance. For example, the open source low cost entry level printers typically don't have any significant service at all. But some of the more expensive systems can have annual service contracts in the tens of thousands of dollars. Another factor to consider is how many parts on the system are not covered under an annual service or maintenance agreement. On some systems, some fairly expensive components wear out and are not covered under a typical service agreement. Look at things like print heads, for example. Do they wear out? How often do they need to be replaced? And what cost are they? Are they included or not included under warranties or after warranty service and maintenance agreements? And look at the other consumables. There may be build platforms that are consumable on one system. Another system may not use build platforms. Are there chemicals that have to be used at the end of building the parts to remove the supports? Or do they just melt away or dissolve away in a non-chemical environment? And then finally, labor. And labor is important because some systems are kind of push-button in operation. Others require quite a bit of job setup. Is there routine cleaning and maintenance that has to be done before, during, or after a build job that's going to take labor time? How long does it take to get the supports off? How long does it take to prepare the part for its final use? These are all things that you need to consider because there are real costs involved with owning your own 3D printer. And finally, what I want to suggest is that there is no single 3D printer that does everything. And you really need to determine your applications that you're going to use it for and look where you're going to get the greatest benefit. You may gain a benefit from getting multiple 3D printers. You may get a professional system and a low-cost system because of the different conveniences and capabilities it provides. And don't forget about the availability of outsourced services. Oftentimes, you may have a specialized part that you need on an occasional basis that cannot be produced on a technology you're looking at. And you may be considering buying a much more expensive printer than you need when, in fact, you could continue to use outsourced services for specialized parts when they're needed on an infrequent basis, and that will probably be a better economic decision for you. So make sure you pick the right tool or combination of tools for the job you have in mind. And just in closing, I want to thank you. This is my opportunity to give a little plug here for 3D Systems. We offer a broad range of 3D printers in the personal, professional, and production categories. We also have a 3D Pro Parts service that can provide specialized parts when you need them. And you can reach us if you have any desire or questions or would like to explore further how one of our systems might assist you. You can go to www.printand3d.com and contact us through the website, and we'll get back to you, and one of our professionals will help you sort through all the maze of all the things that are out there to help you choose the right printer for your job.
Thank you, buddy. I appreciate that. Okay, next we were going to hear from Scott Harmon. He's Vice President of Business Development at Z Corporation. An electrical engineer, Scott is responsible for expanding sales in current channels and finding new applications for Z Corporation products. Scott?
Hi, Leslie. Thanks for the introduction. Thank you, everyone, for attending today. We hope that this session is informative for all of you. I think Buddy had some great comments, one of which is that that most of the 3D printer systems on the market today are very, very different. The market benefits from having a range of different technologies that deliver different benefits. And so understanding those technologies and understanding your application is an important part of thinking about what three-dimensional printer to buy. Today, I'm going to talk about Z Corporation Z printers. Z Corporation is outside of Boston. We've been in the 3D printing business since 1997, and we manufacture a range of three-dimensional printers that range from kind of the entry level at about $14,000, $15,000 a piece, up to larger production systems that are in the neighborhood of $60,000. Notice I'm having a little bit of a problem advancing the slide. There we go. So what I'll do today is I'll give you an overview of how the operation of Z printers works. So we'll talk about the way the printer itself functions. We'll talk about some of those same benefits that Buddy outlined. It was a good review of some of the key characteristics of 3D printers, and we'll talk about where the Z printers perform on a lot of those things and what we're known for. And then in conclusion, we'll talk about where Z printers best fit in the design process and what kinds of applications are especially good for Z printers. So the printer itself operates in 3 easy steps. The first step is that it deposits the build material. In our case, the build material is a plaster composite, not dissimilar to the kinds of materials that are used for dental models or stones. It spreads a very, very thin layer of that material, about 4/1000ths of an inch thick, in a nice even layer. And then it uses inexpensive inkjet print heads to basically solidify the cross-section of the part that you're going to make in the powder, so that you have a part that is kind of bound together, glued together, and then you have the loose powder around it. At the same time, one of the things that makes our printers unique is that the 3D printer will actually print the surface in color. We have 3 and 4 color printers so that you can achieve tens of thousands and hundreds of thousands of different colors, from the primary colors all the way through secondary and tertiary colors. Again, that doesn't cost anything in terms of time. It's all done at the same time that the part is printed. So again, the operation is relatively simple. The advantage of being able to print a layer at a time is that you can generally print quickly, and that's one of the things that the technology is well known for. So whether you call it capacity or speed, it kind of comes out to be the same thing. In general, we print at about 0.9 inches per hour. Certainly if you fill a build up, you can make it take a little bit longer than that, to Buddy's point. But because most of the process is layer-based, it prints quite quickly. You can do multiple parts in all axes, which is relatively unusual in this business. And as I mentioned, you can print multiple colors all at the same time. This particular sample build has 7 parts in it and consists of about 100 cubic inches worth of parts and would take about 12 hours to print on our printers. So speed, capacity, the ability to print lots of parts is one of the key benefits for Z printers. The second key benefit that Z Corporation is known for is, as I mentioned, being able to print in full color. I think Buddy made a nice point that a lot of people in the design process are thinking about how to use color. Color is a very, very important element of design for lots of different kinds of products, and being able to apply accurate color as part of the 3D printing process has significant advantages, obviously, versus having to paint the product later. The resolution is very, very high. You can see the printers will print all the way down to 4-point font, which is really very good resolution, especially when you're talking about the 3D printer class of products in this industry. We'll talk about cost. Buddy, I think, made a great point that certainly you should have your part printed on the technology that you're interested in, the technologies that you're interested in, and you should make sure that that you understand the total cost. There are certainly lots of different kinds of quotes to cost, and they vary differently depending on the part geometry and the technology that you're printing on. One of the things that is unique about Z Corporation is that the 3D printed parts can be adapted to your application. So if you're just looking for a very, very quick concept model that you want to show to somebody and plan to throw in the trash, you can essentially print it in draft mode and get very, very low cost. You can also print in basic color for moderate cost or print functional parts, or you can choose to do full-fledged presentation models with very, very high definition color and resolution. The good news is that you only pay for what you get, whereas most technologies, you're basically tied into a certain class of materials and a certain cost for those materials. One of the things that Z Corporation is not terribly well known for is materials. As I mentioned, the parts are made out of a plaster composite. It tends to be relatively strong. It has very high compression strength, reasonable tensile and flexural strength. However, it's very rigid. There's not a lot of flex to it. It doesn't have the bend that plastic does. Having said that, for many different applications, you could consider metal parts, some of the more rigid plastics. It actually creates a pretty reasonable facsimile to the intended material. You can see on this page we've got a zip line that was 3D printed, a sprinkler head, a chassis, and a mechanical chassis. We've actually printed skateboards with our 3D printer and ridden those skateboards. So the parts can be made to be functional for specific types of functions, and so you shouldn't accept that a printer generates functional parts or not functional parts. You should think about what is functional for you and what kinds of material properties are important for your application, and then make sure you can get those from the printer that you're interested in. So where is Z Printer typically a great fit? First, at design-intensive companies, places where the pace of design, the diversity of design is very, very high. Places with lots of CAD seats, with very, very demanding product cycles. Shoe companies are among the more famous examples of these. When you think about shoe companies, they generate hundreds and hundreds of SKUs, and they generate new variants literally every few months. And with that kind of speed, it's very, very helpful to have a system that is fast and that is economical to operate, and Z Corporation is known for both of those. When you think about getting beyond just pure engineering applications, so more and more 3D printers basically started out, rapid prototyping machines started out very much as the tool for the engineer or the designer. What more and more companies are figuring out is that 3D printed goods can be very, very helpful far beyond the engineering organization. They can be very helpful in sales and marketing and market research, getting feedback from customers, having communication with manufacturers and things like that. And the extent to which your organization wants to push 3D printing out into consumer or market-facing applications to use them as sales samples and demonstration kits and things like that, it can be very, very helpful to have a printer that, again, is very fast, low cost to operate, and obviously the use of color can be extremely important there. Finally, office friendliness. Be clear about the site requirements for the 3D printer that you're interested in. There are a number of 3D printers out there that require pretty extensive modifications to a site based on disposal requirements, plumbing hookups, things like this. One of the advantages of Z printers is that there is very, very, very little waste in the system. All the loose material basically acts as the support material. There is no support material required. It all basically gets recycled back into the system, and so there's no waste to the system. This means a couple of things. Number one, it brings the cost of the 3D printed goods down. But number two, it means that you don't have to worry about where to store waste, whether waste can go down the drain, whether somebody needs to come pick up your waste, etc. And so make sure that you understand the type of facility that you're working in and the kind of machine that will be the best fit for that kind of facility. So I thought I would finish with a couple of examples of companies that are active users of Z printers. The first is the Cisco Consumer Group. I think everybody is probably familiar with Cisco systems. Cisco has obviously a world leader in routers and networking technology. They have a very large consumer division, and what you can see there on the right-hand side of the screen is the literally hundreds of 3D printed parts that they're making in their consumer division to make sure that the designs that they're putting out to consumers meet the needs of those consumers. And so they conduct extensive market research, and they have marketing and sales and market research and customers involved in the design process. And they iterate very, very quickly. They print new models all the time. They mark up the models, they write directly on them, they make modifications, and they print new models. And so having a 3D printer that creates models quickly, that creates models inexpensively, was very, very important to them. And you can see that it's made a big difference to the way that they do their design process. Kind of on the other end of the spectrum, one of my favorite companies is a company called Spirax Sarco. Spirax Sarco is very much an industrial company, not a consumer products company. They're a leader in steam-related products and services. They build heat exchange systems and pumps and all kinds of amazing things. They bought the printer initially as an engineering tool to design these systems. A lot of their systems tend to be custom systems. And what they found was that in addition to being a critical engineering tool, it was enormously useful as they sought to take their products to market. And whether they were at trade shows or whether they were putting salespeople on the road, they were giving them 3D models and using these 3D models to help demonstrate the technology that they had developed. And again, clearly having a low-cost system, a very, very fast system, and a system that prints in full color is one of the things that that helps them to be successful as they push 3D printing out beyond just the engineering organization. With that ends my presentation. Again, thank you for attending today, and we look forward to hearing from you.
Thank you very much, Scott. We appreciate that. Now we will hear from Fred Fisher, Director of New Business Development at Stratasys Incorporated. With over 10 years at Stratasys, Fred has held a variety of titles and responsibilities, including Senior Applications Engineer, Product Manager, and Product Marketing Manager. Fred has educated many engineers and managers on how additive manufacturing can revolutionize their business and benefit their bottom line. Fred?
All right. Well, thank you, Leslie. I just want to thank everyone again for attending, and our goal here is to give you guys an informative presentation that helps you really match the right technology with kind of the application, budget, and other needs to your organization. My presentation will have some of the similar themes that you've heard both Buddy and Scott talk about already. So what we'll do is we'll go through an overview of what we believe are the different categories of types of technology for additive manufacturing, a high-level look at the types of applications that additive manufacturing systems are utilized for, cover a couple success stories of how companies have matched the right system for their application needs, and then really wrap up by talking about some final decision-making process thoughts and needs. So to start out with, just to reconfirm, kind of our solution classification comes in 3 buckets, somewhat similar to what you've heard about before. The first of which are really what we kind of call on-demand services or service bureaus, right? These are a little bit like kind of the Kinkos of the industry, right, where consumers or engineers can come to an organization that owns a piece of equipment and give them their design, and in exchange for cash, essentially get prototypes or manufactured parts in exchange. Generally, service bureaus tend to be the areas that new users or new engineers to the additive manufacturing world sort of incubate their need or get some experience. Once they've grown beyond that, then they really look into the type of different systems that can satisfy their needs. And there's 2 categories. There's a little less granular than what Buddy presented, but really kind of what we call 3D printers. These are systems that are really optimized or maximized for affordability so that they can be available for the broadest reach of the engineering audience. And then the other end of the spectrum, you have what we call our 3D production systems. These are systems that are really maximized or optimized for performance, and as a result of the performance, they are capable of the broadest range of applications or have the largest capabilities of systems. Now, when we switch and think about how the systems are actually used or the applications, over the last 20 years, the industry's been around for about 20 years, and as I think Scott alluded to, and so did Buddy, the applications additive manufacturing had been used for over the last 20 years predominantly resided in the design community, things such as concept models and functional prototypes. Concept models being simple parts that evaluate really kind of form and fit for an engineer. And then functional prototypes, as the name suggests, is really a part that the engineer is able to actually functionally test their product in the environment. And again, this is really where the companies have grown and technology have been used over the last 20 years. In the last really 3 to 5 years, both the performance of the technologies as well as the awareness in the marketplace has grown, and it's expanded the usage of these technologies beyond just design, but also deeper into the manufacturing product development, the manufacturing side of the product development cycle. And specifically, the 2 categories of applications that we often refer to are manufacturing tools and end-use parts. Manufacturing tools typically being things like jigs, fixtures, check gauges, drill guides. They're really parts that are out on the production floor that help assemblers and manufacturers manufacture their actual parts. And end-use parts are really then actually producing those parts then. So instead of using traditional tooling and machining to produce the part, actually using additive manufacturing to produce parts. And this generally tends to be relevant in kind of the low volume production areas. So if you take the system types and then the applications and lay them on top of each other, there's sort of this continuum that occurs. And as you move your way from kind of the left to the right, from concept models to functional prototypes, manufacturing tools, and end-use parts, generally what happens is the performance requirements of the application increases as you go from left to right. And from the very broadest sense, what we see is when end users or when engineers are trying to evaluate what type of system is best for them, whether it's a low-cost 3D printer or a high-performance 3D production system, it's really about marrying their application need to the system's performance capabilities. And the deeper they get into the design cycle, or the more they want to do things such as advanced functional prototyping or manufacturing tools or even end-use parts, the more logical a 3D production system becomes for them, or the more that they can justify the capabilities of those 3D production systems. And in order to kind of articulate that, I want to share just a couple very quick success stories from our end users around the world. One owns a 3D printer and another that has a 3D production system. The first company is a Canadian-based manufacturer of spas and small pools called Arctic Spas. And traditionally they had been outsourcing their prototyping needs. They'd been working with a local CNC and additive manufacturing service bureau to outsource prototype parts for their latest spa designs. And a number of both engineers and senior management folks in the company started to grow concerned about the sensitivity of sending out their latest and most confidential designs to a third-party organization. And in addition to that, as the business grew and as the amount of products that they put in the marketplace grew, their demand for prototyping grew, and they were able to begin to evaluate justifying bringing a system in-house. So when they did that, they really took kind of a hard look at what their application requirements were. And naturally, as you can imagine with the applications around the spa, they needed parts that could survive kind of both hot and cold temperature extremes from negative 40 degrees Celsius upwards of over 100 degrees Celsius, and parts that could survive exposure to water as well as high pressures in the neighborhood of 20 to 25 psi. So they really needed a system that could do not just concept modeling, but really kind of some light-duty functional prototyping. So for them, owning a 3D printer was really kind of the right solution for them. They didn't need all the performance characteristics of a 3D production system, so they could justify bringing a lower-cost system in-house to really satisfy their application needs. And like with all design, or many of the design-related applications, really the benefit for Arctic Spa having a system in-house, of course, number one is being able to maintain the confidentiality of their designs, but also what it does is it allows their design engineers, of course, to validate their designs before they go to production tooling and to make and find the changes to design before they go to production tooling, of course, when it's more costly and time-consuming to make those changes. The next example I want to give is a company called Gibbs Racing. A number of you may be familiar with Gibbs Racing. They're a company based out of the Charlotte, North Carolina area, and they've been a long-time user of our technology, and their design engineers have a real unique problem. Typically when they start experiencing a problem on the track, their design engineers don't have months or years to fix a problem. They have days. They literally have 3 days to fix a problem. And in this particular case, a number of their teams were having premature tire failures out on the track that were causing, of course, the cars to crash and either to, of course, lose the race or even be knocked out of the race altogether. And this happened on one particular track on a weekend. So their design engineers generally, the car comes back from the track on Monday morning. The design engineers really have from Monday morning until Wednesday afternoon or evening to determine a solution, validate a solution, and then to put that solution on the vehicle itself, and then to get the car in the hauler and to send the car to the next track for the next week. And this is a case where, of course, time was one of their biggest requirements here at Gibbs Racing. So these the engineers had a theory. They validated the theory very quickly by producing a concept model that was produced in the system to blow additional air across the brake duct, the brake caliper, and onto the actual bead of the tire itself. The tire had been overheating from heat from the brake caliper itself, so they were able to create a very quick concept model, put it onto the car, and do some quick testing and validate that that indeed was could be a valid solution. From that, they actually improved their design, or they optimized their design to fit in the space. The space inside the wheel well, as you can imagine, is quite tight with mechanical components for the race vehicle itself. So they came up with a design that was really optimized to fit inside the space and to blow a maximum amount of air across the tire bead. Of course, keep the tire cool and to prevent it from blowing out. From that, then, they created not a concept model, but they used a different material from our system to produce a functional prototype that could withstand the temperatures around those actual brake calipers themselves. So they used a different material that was able to withstand higher temperatures. And they took the car out on the track and actually tested the car with and without the brake duct and validated that indeed this was the solution that they were looking for. They did all this by Tuesday afternoon. Tuesday evening, they actually produced what they call tooling bucks on their system, and they produced fiberglass molds from those tooling bucks, and they were able to produce a carbon fiber part and actually put those on the car by Wednesday afternoon and put the car back onto the hauler and send it down the track. So again, for Gibbs Racing, time is really the biggest challenge for them, and they were able to take what normally would have their engineers would have spent over a month if they were outsourcing and working with external vendors, and do it in-house in a matter of 3 days and for dramatically less cost, which again are cost and time are two of the primary benefits of utilizing additive manufacturing from kind of the broadest sense. So again, in their case, the ability, the capabilities that the 3D production system had for them in terms of being able to produce parts out of multiple materials allowed them to use the system not just for a simple kind of form and fit concept model, but also for a functional prototyping, for a functional prototype as well as a manufacturing tool. So for a broader set of applications in the design continuum, and as a result, they were really able to compress their time down. So with that, just kind of some final thoughts on selecting additive manufacturing systems is I think both Buddy and Scott alluded to, really the biggest thing is really understanding what your application requirements are. What are you trying to do? And as they've both alluded, every different technology does things well, and there is no one technology that fits all. So really understand what your application requirements are, and then do a good, robust search and find the right technology that marries the capabilities to your application needs. And typical selection criteria, obviously thinking about where you may want to put that particular system, such that it's located to be conveniently accessible for the engineers that will be utilize the system, whether they're design engineers, multiple design departments, or manufacturing engineers. Naturally, the material capabilities or the actual output of the system is important in terms of the environments that the part can withstand. And as Buddy, I think, alluded to in the very beginning, really understanding the entire process from kind of design file or STL file to the actual prototype in your hand is very important as well. Or that entire the entire process, the amount of labor, time, and steps in the process that takes. So make sure you really do get a deep understanding of that. And my final note is, no matter where you are in your decision-making criteria, we always think that there's no better way to experience additive manufacturing than to put your part from a technology in your hand. And we, Stratasys, are always open to and very highly interested in producing your parts in our technology and putting that into your hands, because we think that's the best way to understand what the technology can do for you. I suspect all the other manufacturers on the line do the exact same thing. So no matter where you are, that's the one call to action I'd recommend is get a part produced from a system and see just what it can do for you. So with that, I'll turn it back to Leslie.
Thank you so much, Fred. Okay, and finally we are going to hear from Jerry Barbarian for Objet Technologies. Jerry provides application guidance and expertise to rapid prototyping professionals across various industries, including automotive, consumer goods and electronics, medical, and others. He is the focal point of Objet's North American Customer Research Program and is responsible for gathering field intelligence for the R&D and applications departments based at Objet's headquarters in Israel. Jerry, you now have the mic.
All right, thank you very much, Leslie, and thank you all of DesignWorks for giving me the opportunity to speak to you. As Leslie said, I work with sales operations, and I'm an applications engineer for object geometries. Let's see how these slides work. Generally today, what I'm going to talk to you about is a little bit about object geometries and the technology itself. I think all of my colleagues have done an excellent job talking about why you would want to bring which technology in-house and how to basically go ahead and look to see what kind of application you're going to be focused on before you pick a printer. So what I'm going to start off by doing is just telling you a little bit about Objet. We're a leading solutions provider of high-quality, cost-effective, three-dimensional printing systems. Of all the relevant Fortune 500 companies that can use 3D printing, 80% of those companies use Objet. We have customers from General Motors to Boeing to Northrop Grumman, Apple, Sears, and so on. As of right now, we have an install base of just over 2,600 units, and that's worldwide. What I want to show you on the next slide is a little bit of where our locations are. So we have these slides, there we go. We have offices in the U.S. That is where I am. I'm just outside of Boston right now, enjoying the snow. We have offices in Europe, in Asia Pacific, in Latin America, and our corporate office in Israel. Across the bottom, I have just some of the numbers of people that we have working at Objet right now, and you'll notice that the largest amount of people we have is in research and development. And I just want to spend a moment saying that here at Objet, we focus very much on research and development and investing a lot of our money back into finding better technology and furthering Objet's technology. Now, the reason I go ahead and wanted to explain a little bit about who we are at Objet is because we understand that when buying technology, we're not just buying a machine. We're also buying the company behind the machine. We want to know that 2, 3, 4, 5 years down the road, that company is still going to be there and producing cutting-edge technology. So to lead in, let's talk a little bit about Objet's technology. Our core technology is inkjet printing. So we take 2D inkjet printing, which comes from the 2D printer world, whether it's an HP printer or a Canon printer, anything that you would hook up to your computer at home and print on. And we transform that into 3D printing by adding a third dimension in our Z-axis. Now, we view that as a very scalable technology because what we do is we piggyback on top of the billion-dollar 2D printing industry, and by adding a third dimension, we're able to use their technology and move that into Object's 3D printing technology and our inkjet technology. So on the next slide, what I want to talk about is Object's single material printing technology. So the way our technology works is we have a print head. Depending on the model, we have different number of print heads. Print heads are laying down a liquid resin. It's a photopolymer, so it's cured with UV light. And as the head moves back and forth, we're laying down this resin, curing it with the light, and it's laying it down at about 16 micron layers. We build one layer on top of another until we get the actual part. Now, we also have a dual material technology. So our Conex technology is the only technology on the market that can print two materials at once. And what that allows us to do is to take any one of our 10 materials, which I'll focus on in a moment, and it allows us to print two at the same time, or we can take those two and blend them together to get new digital materials. So what that brings us to is this picture here, which I like to call Object's business card. And what we see here is one piece that fits into another and a screw on the left. And what this is showing is that we have incredibly smooth and fine features from our 16 micron layers. We can print thin walls all the way down to 0.6 millimeters or 20 thousandths. Our accuracy can be plus or minus about 4 thousandths. Also, the resolution of the printing, we can get to a 600 by 600 by 1600 dpi. Now, also, we talk a little bit about office environment friendly. You know, we talk about post-processing, support, hookups, and one thing nice about the Object technology is it is a very office-friendly technology. The printers operate with less noise than an actual copier. We have no exposure to hazardous materials, and it becomes a nice office environment-friendly machine. So next what I'd like to talk about is a little bit of the applications you can do with Object. So we hear a lot of talk about form, fit, and function. And what those really are, because Object can do a little bit of all of that. So when we talk about form, we talk about something you can hold in your hand. They say a model speaks 1,000 pictures and a picture says 1,000 words. So being able to hold something in your hand and look at it instead of holding a piece of paper and looking at it. When we talk about fit, we talk about assemblies. Here you see on the right a very interesting piece that Logitech did. It used all of its interior electronics and printed the exterior off an Object machine and made an actual working mouse to test that as a prototype. So when we talk about fit, we talk about assemblies and being able to test things. When we talk about functional testing, we talk about real-world physical testing. So not quite rapid manufacturing, but being able to have materials that are tough enough to print them out and test them. Another thing Object can do is small quantities of rapid manufacturing. We do have production-grade materials for hearing aid and biocompatible. Now, when we talk about applications, application is not always just technology. There's a lot of different industries out there that have applications that can be used for 3D printing. For example, Object's used in the entertainment industry. And here you see there are two great movies, Avatar, which won the Academy Award for Best Art Direction and Best Cinematography, and also Coraline, which was nominated for Best Animated Feature Film. And both of those films were developed and filmed using Object's technology. So we get to the actual products. Object has 3 different families of printers. We have our desktop printers, the Object 30 and 24. we have our professional line, and then we have our Conex family. So we'll talk a little bit about the desktop printers. Generally, when we talk about desktop printing, we talk about smaller, affordable systems. Our Objet 24 has been released just a little while ago at 19.9, and that's new for Objet. We have not been a big player in the desktop market up until about a year or so ago, and now with a new low-price machine, we're basically bringing the professional line technology all the way down to something that's affordable for our desktop machines. The next family we have is our Eden family. And we have a variety of these machines which are on our professional line. And these professional machines range mostly in platform size. The third family we talked about was our Conex family. The Conex family is our dual material printer family. So we have two Conex machines, the difference being the size of the build. And these machines allow us to do a variety of things. We can do overmolding, a variety of different applications while using two materials. Now, I've talked a lot about our materials, so I wanted to show you a small chart of the materials that we have at the moment. We have anywhere from general purpose materials to polypropylene-like materials, ABS-like materials. We have rubber-like materials. And then we also have hearing aid materials. One nice thing about all of our materials is that they all use the same support. Changing the materials is very easy. They come in cartridges. And that way you can use, say, our general purpose translucent material. And if you want to switch to an ABS or a rubber material, it's a very simple material change that takes about 30 or so minutes, and we don't have to remove the support. We use the same support. Now, we do have some new materials coming out. And what I wanted to touch on a bit was some of our new materials. So we have a new material called Vero White Plus coming out, and that is going to be a new white material for our desktop machines. It has wonderful dimensional stability. We also have a new clear material coming out. Now this is a true transparent material that we can reach a water clear finish with. Next we have a high temperature material. This material is wonderful for static parts and thermal testing. And then lastly, which is new for Objet, is a true ABS-like material. And this material is able to simulate engineering plastics where Objet has never really been able to go before. The way I like to think of Objet is that our technology is pretty amazing, but the materials have been where we were somewhat held back. And now with the release of these new materials, Objet's really pushing itself into a whole new realm. So I mentioned a bit about digital materials. Right now on our Conex, either the 350 or the 500, we have the ability to blend our 10 parent materials or full care materials together to create up to 48 different digital materials. Those can be rigid and rigid materials, like we see on the faucet here, or we can do rigid and flexible materials. Here we see a bicycle with a rigid frame and rubber-like tires. So there's a variety of applications you can do by blending two materials together to get our digital materials. So thank you very much.
Okay, thank you very much, Jerry. Now we're going to open this up to questions and answers. If you have a question, please feel free to go ahead and enter it onto the question panel that you have on the side of your screen. We do have a couple of questions that have already come in. One of them is, what are the capabilities of 3D printers in terms of building porous materials? Anybody want to address that question?
I'll take that. I think I won't say we're the only one, but certainly our materials when they come off the printer are porous and and can be used for things like vacuum forming and stuff like that without much modification. I think most of the, you guys tell me if I'm wrong, but I think most of the other ones are not porous materials, but feel free to chime in.
Yeah, this is Fred Fisher with Stratasys. Both our 3D printers and our 3D production systems, the user has a relatively simple choice to either produce the part solid, which generally tends to produce a part that's stronger, or to consciously choose the part with sort of a honeycomb interior style, or that we open up the porosity inside the part, which generally tends to drive the build time and cost down, and also opens up other applications, as was mentioned earlier, like thermoforming as an example. It makes those much easier to use. So,
yeah, and this is Buddy at 3D Systems. Our bits from byte system is also able to get some porosity in the way you build, but our Projet and Beflash products, we're kind of the exact opposite. Our systems produce watertight parts, so if you need to use these for extended water use and you don't want the parts to swell or things like that, ours are kind of the exact opposite.
Okay, we have a question here specifically for Dimension for Fred. So will Dimension be introducing a sub-$10,000 printer?
Well, certainly the specifics of our product development, futures, we don't typically comment on that, but, I'd let kind of the history be kind of a indication of where we're headed as a company, and I think where the broad industry is headed, right? All of the presenters today talked about, or many of them talked about 3D printing, and really one of the key driving points with 3D printing is continuing to drive that cost down efficiently, such that it can be affordable for a broader range of engineers and users. So while I can't say what we're going to do specifically, that's certainly the direction that we, from a new product direction, are headed in, right?
Okay. And another question, I think, for you, Fred. Was the brake duct actually used on the car at Joe Gibbs just fit checked?
So for Joe Gibbs, the brake duct that they used, the concept model was just a kind of a quick test to determine if it would indeed work or not. They created a functional prototype out of a different material, a higher temperature material from our system, one that was able to withstand the temperatures around the actual brake caliper itself. And then they created a tooling master that they created carbon fiber parts from. So the actual parts that went onto the race vehicles themselves were manufactured out of a composite material, but they were made off of a tooling master from the FDM technology. So it really, in their case, it was a concept model, functional prototype, manufacturing tool, and then they used, I guess, kind of a hybrid of a traditional manufacturing process to produce a composite part that went on the vehicle itself.
Okay. This one is for Buddy. Does the BFB model have a support material head?
Yes, it does, and that's actually, you can configure it when you purchase it, and you can put up to 3 heads on the system to run, 3 different materials.
Okay, excellent. This question is for Z-Corp. Was the last Z-Corp model painted, or was it right out of the machine?
I don't know off the top of my head, to be honest with you. Those colors are certainly achievable on the machine. The silver would usually require painting. Things that are shiny and metallic have to be done with paint, but the other ones can come off the machine. I don't know off the top of my head for that particular model.
Okay. The next question is, can each system allow a pause during part buildup to insert other parts, like a steel ball bearing in a housing being built?
This is Fred Fisher at Stratasys. Our technology, both for the 3D printer and the 3D production systems, gives the users some capabilities to do just that, to pause the system, to put inserts into the part. Ball bearings may be one example. Sometimes they're drill fittings. Others put RFID tags or other mechanical components inside the parts themselves. So the FDM technology does allow that to happen. With our 3D production systems, the users can actually control the tool paths themselves to really optimize that to happen even better, right? They can create cavities that accept a broader range of geometry and materials to go in the part itself. So yes, the FDM technology can do that.
Okay, here's a question that's going to get all of you talking a little bit. How do the additive manufacturing processes affect end material properties?
Well, I'll maybe this is a Fred Fisher again with Stratasys that, to some extent it starts, I think it starts out a little bit with the raw material you're working with. In our case, of course, we have, thermoplastic parts themselves. So the thermoplastic parts cycled through our process are relatively similar to thermoplastics going through injection molding, with the exception of the fact that we're building a part in a layer-by-layer fashion. But there's not massive stresses induced from that heating and cooling process, or that would be any different, let's say, than running it through injection molding.
Yeah, this is Buddy at 3D. That's a very broad question,
Yeah.
but one of the applications that we see is people wanting to vary the look of the part surface, and with different build styles you can achieve either a slick glossy surface or you can achieve a matte finish type surface on parts, and you can also get some varying elongation and tensile strength depending on which build style you choose. And obviously, if you go to systems like stereolithography, there are numerous process controls you have to affect part, outcomes and part property outcomes.
This is Jerry from Object. It's a very interesting question. I feel like the question is, do we have homogeneous materials? And the question from at least from Object Technology is that we're using such thin layers and using a liquid that comes out first as a liquid when it's laid down and then is cured with the UV light to become solid, is that our layers actually do bind about 3 layers deep. So even though they're not in rapid prototyping, nothing is completely homogeneous in all directions, we do achieve something that is very close.
Just a quick little comment for everybody here. We will be doing another webinar sometime in the early spring or late middle spring about materials for 3D printers. I have another question here, and this is also on materials, but this is, will there be any new materials for FDM?
Again, this is Fred, obviously, with Stratasys. Again, a little bit like with the question around 3D printing and when will we break the $10,000 barrier, the specific materials that we are running through our R&D process to commercialize are still confidential at this point, but just like with the Object team, we have a very aggressive materials R&D department that's working on commercializing some materials for the 2011 timeframe. So we indeed will have some material announcements, but the specific materials, it's probably a bit premature to announce what specific they are until they're completely available for the system.
And we have time for one more question, and this one is for Object. Can Object create pieces that can be exposed to the weather, such as rain? And can you make end pieces out of the materials that you use?
That's a good one. Okay, so for the first section of that, the answer is yes, absolutely. There is, first of all, pieces that come directly off the printer that we've used in all kinds of hydro testing, rain, water, any kind of fluids. There's also a certain amount of post-processing applications you can do, whether it's just a a simple lacquering on a part that completely seals it. So absolutely those pieces can be used in any sort of weather or water environment.
Okay. Now for those of you who still had some questions that we couldn't get to, you see the information on your screen. You can send your questions to each of the respective companies. There have been a number of questions on will this recording be available, and the presentation will be mailed to everyone later today, and it will also be available at www.designworldonline.com. And again, we would like to thank every one of you for attending this webinar from Design World. We hope you've enjoyed the presentation. Thank you, and everybody have a good day.